chapter 2 on, oh, you got it? Oh, great, thanks. We're on chapter 2 on functions, right? I've introduced, a couple different ways to look at what a function is. And so a lot of times we like to look at a function in terms of a graph, right? So then a natural question is, given a graph, is it possibly the graph of a function, right? And so let me just throw some examples on the board here, and I'll ask you guys to tell me, oh, come on, really? There's chalk back here, haha. Here's the question, is it the graph of a function game? All right, so example 1, we could do there we go. And could I enlist your services again? Oh. Uh-oh. Just to remind me I'm short, I think. It's a conspiracy against me, you know. No, probably not. Let's see here. Example 1. What's that? So if I had a graph that looked like this, it's just the graph of a function. What's the graph of a function? What is that by definition? What does that look like? Remember, graph of f equals to x, comma, f of x, such that, x is in the domain of some function. And so the key property of a function is that it's single valued, right? F of x can just be one thing. So if we have the graph of an alleged function, we can apply the vertical line test to it, right? And so like here, okay, right, just 1 point. But when we get over here, we're in trouble, see, because that vertical line hits 3 points, and that would mean that one input would have to give 3 outputs, which is not the definition of a function, right? It's not a function. Example 2. We could have like this. And suppose that it's going from -2, -2, all the way over here to 2, 1. And let's suppose that this is 1.5. So first question, is it a function? Yeah, it is, right? Any vertical line we draw through the graph, we just hit 1 point. That means we assign a unique y value to each x value in the domain. What's the domain, by the way? Nope. What was that? -2 included, right? To where? To 2, also included, because I put solid dots at the end. What's the range? $1.5, right. What's the codomain? You see, we're not talking about that anymore, right? That's just some crazy nonsense you made up in the first lecture about functions. We don't find it anywhere else in the book. No one else talks about it, right? That's just your problem. No? Pretty much, yeah. So maybe some of you will be math majors. Who knows? It's possible. You could put the codomain as all reals, right? Or really any superset of 2 minus 2 to 1.5, anything that's bigger than this and includes that will work. Yep. Example 3. So sometimes we're not given a graph. We have to make a graph, right? So like we could look at the solution of x squared, plus 4x plus y squared equal to 0. And we know how to graph that, right? How do we graph that? We complete the square. And so that has to subtract 4. And so what we have is x plus 2 squared plus y squared equals to 4, which is, of course, 2 squared, right? So this is a what? This is a circle centered where? It's at, centered. Looks like minus 2 comma 0, right? So the center's right there. And the radius is 2, right? So it looks like that. Is this a function? I mean, is this the graph of a function? Again, no, because it fails the what? Vertical line test. So, nope. Not graph of single function. So to decide whether or not something's a function, we can apply the vertical line test, right? But what if you're not given the graph? How would you decide whether or not a given equation could be the graph of a function, right? Like, what's another way to write the graph of a function? Oh, man. I have to be careful. I've only got so much to work with. We could also write this as x comma y, such that, x is in the domain, and y is equal to f of x, right? So like that's another way of understanding what the graph of a function is. We can solve for y equals f of x, where f of x is just one thing. So if I was to attack example 3 algebraically rather than graphically, how could I understand that this is not the graph of one function? How would I do it algebraically? Example 3 without graphing. We have x squared plus 4x plus y squared equals to 0. And so basically the thing we do is to solve for y. If you have an equation, if you can solve for y and you get a unique formula for x, then it follows that you're looking at the graph of a function. If you can't, then it might not be. It also might just be that you can't do the algebra, right? And when I say you can't, I mean that in a variety of different ways. Like, you don't know how to do those particular algebra steps because you haven't done it before. That's one kind of you can't do it. There's another kind which is just like it's theoretically impossible. Just because like the way x and y are like they're so intertwangled, you can't do the algebra. There are examples like that. Don't ask me to come up with one right off hand. I mean, I probably could, but then I would worry about whether or not it's a function. Then we'd have to get out the Desmos here, and we will in a second. But okay, so solve for y. So we isolate y squared, right? And then we do what? Take the square root. So y is equal to plus or minus the square root of And we can clean this up just a bit, right? This is really minus x times x plus 4, isn't it? But the thing is plus or minus. Now you might worry, oh, but that doesn't even make sense because you've got the square root of something negative. Why is that a wrong idea? Why is this not necessarily the square root of a negative number? Why is this possibly real? I mean, I'm thinking of including the square root. A lot of times I have students tell me, oh, it's got a minus, it's negative. Why is this thinking wrong? Right. So your point was that the x times x plus 4 itself could be negative. Right. And so basically, when would this be real? Well, we could figure that out pretty quickly by making a little sign chart. We've got a 0. We've got a minus 4, right? We can think about minus x times x plus 4. When is that positive? Plug in 1. We get 1 times 5, which is 5 with a minus, so it's minus 5, right? So it's negative over here. Whoop, whoop, whoop. And when we go 0, we flip the sign, plus, plus, plus. And then we're negative over here again. So why is this possibly real? Because this quantity is greater than 0 right in here. So this is going to be for what? This sign chart I made here shows you that this calculation holds for what? For x between what? Between minus 4 less than or equal to x less than or equal to 0. But, okay, so the calculation's fine, but the trouble is plus or minus, right? So it's not a single solution for y. That's how we know. Does that make sense that we found minus 4 to 0? Do you see why that is? Look at the graph we made. See, that's exactly where the circle is here, right? So let me replace the question I've originally asked. Is this the graph of a function with a separate but slightly related question? Is this the graph of a pair of functions? Could we find two functions for which the circle is a graph? Yeah, we could, right? The plus gets us the top, and the minus gets us the bottom. So like basically this guy up here is y equals to square root of minus x times x plus 4, whereas the base one here, the bottom loop, this guy down here, is y equals to minus the square root of minus x times x plus 4. Right? Now, the orange or the blue, these separately pass the vertical line test, right? Because if you think about a vertical line, it only cuts through the blue just once. And think about it, it only cuts through the orange just once, right? So the half circles, those are graphs of a function, in particular, the functions defined by those rules. Yeah? So I just gave you guys a big, gory list of recommended homework, and I'm actually working problems right now that are related to that. So just to let you know, I mean, I do things, sometimes it ends up a little bit out of order, but there are problems in the homework that are like this. Let me see if I can find them. I know because I just made that list a couple of minutes ago. Man, I wish I had made a note to myself which section I saw those questions in. Oh, I know it's not 2.4. It might be 2.3. Maybe it's 2.2. Ah, it is 2.2. So the thing I'm doing right now is basically the questions I've recommended, numbers 57, 59, 61, 63, 65, 67. These are all the same sort of logic that I've just gone through. In contrast, the earlier problems like 53 and 55 and 49. So basically, section 2.3 has questions like this, okay? So we're essentially in 2.3. Actually, we just finished 2.3. Even an odd is actually discussed way later in the chapter. I just put it in earlier because it just seemed like the right time. Okay, so, excuse me. Are we good? Okay. So one of the fundamental logical tensions in this course is, how do you test graphing in a world where students have graphing calculators, right? Because it's fundamentally disinteresting to say, here's a function, plug it into a graphing calculator, and then copy it onto a piece of paper on the test. This is not helpful for you. It's not interesting for me, and it really doesn't accomplish anything. Because chalk got me. Just a second. Thank you. I need to start chewing gum. I'm okay. It's okay. I got. There's a water fountain out there. Thank you, though. Really appreciate it. Nice catch. Ask yourself, how would an instructor test graphing on a test then, right? Well, I would probably focus more on the part which is conceptual, right? Like how you take a given graph and shift it around, move it up and down, stretch it out. Basically how you take a graph which is given without a formula and take information from that graph and do things with it, right? So I would make sure you understand problems in the homework like that. Those are good questions that are kind of like a test question that I would anticipate. But so we talked about average rate of change last time, all right? So I've already showed you. Well, I guess I didn't fess up, but fine. I should give you a definition. I say we did it last time, but I didn't call it this last time, right? Last time I called it the difference quotient, but it's essentially the same thing. Average rate of change. Well, that's not quite fair. They're related, I suppose I should say. X equals A to X equals to B. So what that is f of X, f of B minus f of A divided by B minus A. In other words, we could say that that's the change in Y over the change in X. And that is assuming what? When I say it's the change in Y over the change in X, I'm assuming that we're saying Y equals f of X, right? So it's the difference of the Y values divided by the difference of the X values that gives us the average rate of change of the function from A to B. I said that's like what we did last time because last time we did like a difference quotient simplification, right? It was kind of the same algebra, same pattern, isn't it? Not exactly, because I did the X plus H in here, right? Fair enough. It's not exactly what I did last time. See, just to complete the thought, the other way you can do difference quotient. So I did the difference quotient for you guys last time using f of x minus f of x plus h, or no, f of a minus f of a plus h divided by h. But the other way to do it is like this, f of x minus f of a over x minus a. Like this is an alternative. Did I show you this to you guys? I can't remember. I don't know if I did this in here or not. I don't think I did. So there's two different ways to look at the difference quotient. One is like this, and the other is this. Now, if I ever ask you for the difference quotient for some function, I should tell you which one I mean. I mean, these are conceptually the same thing, but in terms of a formula, they look quite different, right? But if you look at this, this is what? I mean, you could think about this also as what? The average rate of change from what? From x to a, right? I mean, we could look at it that way. So let me actually work an example with a function in it. That'll make this seem a little bit less mysterious. Let's look at f of x equal to, let's say, 4 minus x squared. That's a nice function. We can understand the graph of that without a lot of work, right? How does this factor? Can you factor this completely?
2 minus x, 2 plus x.
I got a 2 minus x, 2 plus x. What's that tell me? That tells me x-intercepts at minus 2, 0, and 2, 0, right? And what's the y-intercept? Y-intercept is always at f of 0. What happens when we plug 0 into the formula? 4 minus 0 squared, which is just 4, right? So the y-intercept is 4. And so with that, I can graph this thing. Approximately. I mean, this is a rough picture of it, right? And so we could calculate the average change in the function over various intervals. So let's pick some interesting intervals, right? Let's look at the rate of change, let's say from, how about from minus 2 to minus 1? Or, does that sound good? We can look at change. I need to come up with a quicker way to say that. I'm just going to say I'm looking at delta y over delta x for x equals minus 2 to x equals minus 1. Right? So I should look at f of minus 1 minus f of minus 2 divided by minus 1 minus a minus 2, right? According to the definition of average rate of change I gave over here.
So where did the negative 1 come from?
Well, usually I want to make, just as a point of like naturalness, custom, we want to, I guess I should probably say it's customary to take A less than B, right? I mean, we usually judge change like going left to right. You may have gotten into trouble with this yourself at some point trying to graph a line. Like sometimes I think, oh, it's over 3 and, you know, up, it's like over 1 and up 3. And if you're not careful, if you do it like right to left, you'll create a slope -3 by accident. Ever done this? It's kind of that issue. Like we want to read graphs left to right, so we usually think about the B being larger than the A for this kind of discussion. So minus 1 is to the right of minus 2 on the number line, right? Right? Minus 2 is here, minus 1 is here. So this is my B, this is my A.
But you chose that just for the point of working out the problem, right?
Yeah, I just wanted to pick some numbers which are nice to study the change and talk about what it means. That's going to give me a chance to introduce 2 new terms, namely increasing and decreasing for a function. And also, this function has something called a local maximum, right? So these things are described more fully in, I think, section 2 point. I forget if it's 2.6 or 2.7, but all right, so what do? Plug it in there, right? So we've got what? 4 minus 1 minus 4 minus 4, right? Divided by 1. So what do we get? The 4's cancel, right? And we get minus 1 plus 4, I think. So I want to say we get 3. Am I right? Can somebody check me on that? So going from this point to this point right here, which would be what? This point is minus 1, 3, I think. So this point's minus 1, 3. I mean, my graph is not quite to scale, right? If you plug in minus 1 into that, we get 4 minus 1, which is 3. So if you look at the little triangle that you can form right here, right? You can picture the delta y here, and you can picture the delta x here. Delta x is 1 unit, delta y is 3 units, so we get 3 over 1, which is 3, which is what we calculated. How about if instead of, what about over here? What if we look at the change, let's say, from there to there, right? So let's go from a equals to 0 and b equals to 1, right? What's delta y, delta x in that case? F of 1 minus f of 0 over 1 minus 0, which is 4, well, excuse me, 3 minus what? Minus 4 divided by 1. So it looks like we've got minus 1. So the average rate of change going from 0 over to 1 from 0 to 1, we get a change of minus 1, right? So this illustrates something. There's a relation between the average rate of change and what we say a function is increasing, a function is decreasing. Like, how do you define functions increasing and decreasing? Can you say it kind of intuitively with words? I mean, I might say a function's increasing if you look at the graph and the graph is going up, right? A function's decreasing if you look at the graph and the graph is going down. When I say that, you need to be careful that we're reading the graph left to right. Otherwise, what I just said will be backwards, yeah? We have to read the graph left to right. That's an informal definition of increasing and decreasing. So this function's increasing, right, up until the zenith, right? And then it's decreasing. And at the vertex, where we go from increasing to decreasing, we have what's called a local maximum. It's also a global maximum because that's the largest value that the function takes anywhere, right? So these are terms we need to learn, okay? Increasing, decreasing, local maximum, local minimum. I'll try to keep reinforcing those terms as we go on through more examples. But you see that there's a relation between increasing, decreasing, and the rate of change, right? If the rate of change is positive when you take successive points in some interval, then it stands to reason that that part of the function's increasing, right? If you take successive rates of change and they're negative, then that probably means the function's decreasing, right? Now, I don't know about you, but if I have a really complicated function, the idea of taking successive rates of change for like a lot of points, it seems very tedious, doesn't it? Because it's a fair amount of computation, and this is a pretty simple function, right? I should give you the more careful definition of increasing and decreasing. F is increasing on some set, let's say S, a subset of the reals, if A comma B in S with A less than or equal to B implies F of A is less than or equal to F of B. Likewise, it's decreasing on a subset of the reals if AB in the set with A less than or equal to B implies that F of A is greater than or equal to F of B. So there you go. That's like the careful definition, not just with, up and down words. Yeah.
Real quick, what is like the
This one?
not just the one to the left?
What's this mean? Subset. So this is S, which I give extra. I don't know what these things.
What is it?
This? Just a subset, just a set of real numbers. It could be an interval. It could be anything. Like we can define increasing and decreasing for whatever set of real numbers you like. It's most natural when the set is connected in the sense that like it's an interval. It's an open ray, it's a closed ray, it's a half open, half closed, half open, closed interval, open interval. One of those 9 interesting examples we started with. It's most interesting there. But you can define increasing for a subset like this. What happens if the function is both increasing and decreasing? Could that even happen? What would that mean? F of A is less than or equal to F of B, and F of B is greater than or equal to, you'd have both greater, you'd have what? This is less than or equal to that, and this is greater than or equal to that. What does that mean? Do you guys know? What if I have what if I have a number? Suppose I have Pac-Man less than or equal to Ghost, and I also have that Pac-Man is greater than or equal to Ghost. What can you say about Pac-Man and Ghost? They're equal, right? And what does it mean if a function's equal for A and B for arbitrary, like distinct A and B in the set? That would mean that the function's constant. So like constant functions are both increasing and decreasing with this definition. Okay, anyway, enough of that. Let's look at Desmos here for a bit. There is a great, so as we study graphing, yes, we can make a table of values, and we can use a table of values to create a graph, right? While I'm waiting for this thing to warm up, I'll show you that. You guys have probably done this since early high school, maybe middle school even. I don't know. It depends on your curriculum, but it's not a big deal, right? If I give you x and I give you y equals f of x, and I tell you -1, 0, 1, 2, and I tell you that that's 7, this is 6, this is 10, and this is 13, we all know what to do, right? We go -1, it's at 7, 0, it's at 6, at 1, it's at 10, and at 2, it's at 13, right? And so, I don't know exactly what the thing looks like. It could be this, but it's something like that, right? So given a table of values, you can construct the graph, right? And if you have a formula, you can create a table of values, right? Given a formula, you can start making a list of x's and a list of y's by plugging in the values. But this is the sort of I would say this is the brute force method of graphing, right? It's very labor intensive. I always fall back on like plugging in a value to get an additional point if I want to make a careful picture. But it's hard to beat technology these days. But we'd like to not do that, right? Like we'd like to be able to create a lot of graphs and understand a lot of graphs without actually going to the trouble of plugging in points, right? So how can we understand a large class of the graphs that we see in like common applications of science and engineering and so forth? Well, we can do it with basically having a standard list of graphs that we know, and then we can take that standard list and we can kind of move them around. And so that's what I will endeavor to teach to you and explain to you. If I can actually log in here. Come on. I thought this would turn on. Didn't I do it? All right. Come on. Whoa. Go away. Nope, go away. Stupid smartboard. I kill you. Sorry. I shouldn't use violence against the smartboard. Smartboard dumb. Get out of my way, smartboard. Come on. Let me in. Desmos. Where's your start? There's a big start graphing. Oh, I guess I have to click on the graphing calculator button. Fine, fair enough. Can you guys see it yet? No. Now you can see it, right? Okay, so for the purpose of illustration, I want to show you some things here. But section 2.6 has this like bunch of rules. We can basically take a given graph and move it around. All right. I will not be able to communicate those rules to you in the next 10 minutes. But what I can do is show you the basic list of examples we're going to use to like move around. All right. And so I encourage the other section. I'll encourage you guys too. These are really examples that you should have memorized, or maybe memorize is not the right word, but you should know them when you see them. All right. And so there's actually there's a page in here that has. Oh, here it is, page 166. See this page? This page is like super helpful. This page is super helpful, and it's got linear functions, power functions, root functions, reciprocal functions, and the absolute value function. These are pretty much our basic building blocks, all right, for the graphing discussion. It's on page 166, and I'll leave it up here. If you guys don't have a book and you just want to take a picture of this at the end of class, it'll be right here, all right? So, but I would point out to you, I mean, we can look at these right quick, right? Like y equals to x to the n, right? This is what's called a power function, x to the n, right? Now, I don't really expect you to know what x to the 1.4 looks like, all right? That's kind of funky. But if we get to 2, you should recognize, right? X equals 2 is a parabola, right? How about what happens when we get to 3? We have a cubic, right? Let me make it bigger here. What happens when we get to 4? We've got a quartic, right? Y equals x to the 4th. And what's y equals x to the 5th look like? It kind of looks like the cubic again, right? In fact, I think it's helpful to look at, say, y equals to x, y equals to x cubed, y equals to x to the 5th, all in the same plot. See, what we're looking at here is x is here, right? The cube is The blue one, the fifth power is the red one. What happens when we take y equals x to the seventh? See that? It's even further smushed out, right? They all go through -1, -1. They all go through 1, 1, right? Now, my point to you is not that you should be able to graph y equals x. Excuse me. You should all be able to graph y equals to x, like, carefully and completely. Like, that's a line, right? You've known that for a long time. To say that you can't graph that would be insulting to you. I should not say that to you. That would be rude. But, careful graph of y equals x cubed, x to the fifth, x to the seventh, it would take me time, right? I'd have to actually have a graph paper and do it carefully. But what you should be able to do is if somebody says y equals x to the seventh, you should have in your mind's eye, oh, that kind of looks like the cubic. It's just more steep, That's what I'm saying. That's the kind of memorization I'm talking about. For y equals x squared, that's the parabola. X to the fourth, that's the quartic, right? X to the sixth, I don't have a name for. That's this one, right? X to the eighth, it looks like that. So what happens as, as we get larger and larger powers, it looks more and more like what? Goalposts, right? Like, if you went to like y equals x to the 100th, to a pretty good approximation, it probably looked like a goalpost, right? Here, I'll turn everything else off. See that? So if you want the equation for football goalposts, here it is. Assuming that they have a width of 2 in whatever units you'd like to use. Is that right? No? Who's the authority here on football goalposts? I don't know. I don't know. I know that they're not infinitely tall, so that's definitely wrong, right? Like, this is way too low. And it's missing that thing down here, right? They don't just float in midair, am I right? I don't know. You guys help me out. I don't follow sports. Let's see here. We can also look at the reciprocal functions, right? Like 1 over x. This is 1 over x. What does 1 over x squared look like? I call this the volcano function, right? We should know about this one. What's 1 over x cubed look like? It's kind of like the reciprocal function, except it's steeper, right? And if I plotted them both on the same plot, you'd see that the reciprocal function, the black one, is like more shallow, right? The cube, it goes to 0 faster, and it goes to minus infinity slower. Well, excuse me, faster also. Idiot. Me, not you. X to the fourth is again, so basically 1 over x to any even power is going to be like a volcano that opens up. It has a vertical asymptote at 0, which means it goes to plus infinity from both sides, is what we say. And if we have 1 over x to an odd power, we've got a vertical asymptote at 0, but we're going to plus infinity from the positive side, and we're going to minus infinity from the negative side. Right? These are basic building blocks. The other basic building block that we have, and so these are the things we have to like understand in order to do some of the problems in section 2.6. All right, so you got to know what you know before you can move things around. Is what I'm trying to say. This is the absolute value function, right? And this actually brings me to an important point and a apology that I have not talked about these yet, because this is an example of a what? How do you define the absolute value function? What have I not done in here yet? For shame. Seems like every one of your lectures ends with a point of shame, doesn't it? Yeah. Can you guys tell me what's the formula for y for the? I mean, what's the formula for this graph? It's y equals to f of x equals to what? What's f of x in this case? What's the formula? Yeah, absolute value of x. What does that mean, though? Distance of x from 0. Hey, that's not bad. This is the distance of x from 0 on number line, right? That is a legitimate definition of this function, right? But can you guys tell me, I know two other ways to define it. One other way I know is it's the square root of x squared. That's like a stone cold formula for it. But what people usually write is it's x if x is greater than or equal to 0, and it's minus x if x is less than 0. So the absolute value function is our first example of a so-called case-wise defined function, right? Where we have a different rule for different parts of the domain. This particular topic gives students fits. This is always troublesome. And for that reason, I have recommended many piecewise defined function homework problems to try to help you to make sure you get this idea. It's not complicated once you get it, but you need to work on it if you haven't already. We will do more piecewise defined functions as we go on in here. So anyway, next time we'll be looking at section 2.6, basically looking at transformations of graphs. So that's pretty much where we are. And I should have mission 3 for you sometime soon. I'm getting closer to writing it, and 4. Some of the